On this worksheet, we're going to look at 3 different types of carbon nucleophiles that are used in the nucleophilic addition to a carbonyl group. So as a reminder, we're talking about reactions involving the carbon-oxygen double bond of aldehydes and ketones, and we're looking specifically at reactions where we are adding 2 things to the carbon-oxygen double bond. Something gets added to the carbon, something gets added to the oxygen, or nucleophile is being added to the carbon. And like I said, in this worksheet, all of the nucleophiles that we're working with are ones where carbon atom is being added to the carbon atom of the carbonyl group, which means we're making a carbon-carbon bond. One of these reactions is something that we're already familiar with, the Grignard reaction. We learned the Grignard reaction when we were studying alcohols. The Grignard reaction is a method for synthesizing an alcohol. And Grignard reagents, as a refresher, we want to treat them as if they are alkyl groups with a negative charge on them, alkyl groups with a lone pair of electrons on the carbon atom. And that alkyl group is going to attack the carbonyl carbon and open up that carbon-oxygen double bond. Again, this is just a review because you've already seen this reaction. And so the intermediate that we're going to make looks like this. This is the R group from the Grignard being added to the carbon of the carbonyl group. And when that carbon-oxygen double bond opens up, we end up with a negative charge on the oxygen atom. And then that is protonated with, this case I'm using H3O+. It could also be protonated with water. Just one of the hydrogen atoms goes onto the oxygen with a negative charge. And so that gives us, like I said, gives us the alcohol. Another thing that we did when we were learning about Grignard reactions a while ago, we learned how to do a Grignard retrosynthesis. For example, if we wanted to make this molecule via a Grignard reaction, what would we use in terms of what kind of aldehyde or ketone, and also what type of Grignard reagent. When we're making predictions about showing how to make the molecule via Grignard, there's usually more than one correct answer. The carbon of the carbon-oxygen double bond, the carbon of the carbon-oxygen single bond, this is where the carbonyl group used to be located. The Grignard reaction can put any one of these alkyl groups onto that particular carbon. So we could choose any one of these alkyl groups to be the thing that's getting added in this reaction. Let's just say we choose to add this one as part of the Grignard reaction. So that means, since I've made this decision right here, that means this is my original ketone. It's going to be a ketone in this case. I'm going to draw that molecule right there. So I'm looking for a 1, 2, 3, 4 carbon, 1, 2, 3, 4 carbon ketone with the oxygen on carbon number 2. My Grignard reaction Grignard reagent is going to have this alkyl group. That's a 3 carbon alkyl group, CH3, CH2, CH2. And the other portion of a Grignard reagent is just the Mg with magnesium with some sort of halogen like Br. And then we do need to always follow these up with H3O+ or water. So this would be one of the 3 correct answers to this problem. Now, a new reaction that we're going to look at is the formation of a cyanohydrin. In this reaction, we're using cyanide as the nucleophile. Sometimes it's just written as KCN instead of CN-. This reaction is in pretty weak equilibrium, so the equilibrium is assisted by putting a little HCN in there as well. The cyanide ion, the negative charge, is actually associated with the carbon atom, even though it's being drawn over here next to the nitrogen. That carbon, lone pair of electrons on the carbon, are going to attack the carbonyl carbon and open up that bond. And that's going to give us, this is very similar to the Grignard reaction right here. This is our intermediate. And then we're going to follow up by protonating this oxygen. We could use HCN for the protonation if we wanted to, like that. And that will give us this molecule right here, which is called a cyanohydrin, a molecule that has a cyanide and an OH group on the same carbon. Here's another example. This time we just want to predict the product of this particular reaction. So we're predicting the formula of the cyanohydrin. Our carbon-oxygen double bond is being converted to a carbon-oxygen single bond. The cyanide is being added to the carbonyl carbon, and we're putting a hydrogen on the oxygen, making the cyanohydrin. Now, the last set of reactions that we're going to look at involving carbon nucleophiles are called the Wittig reactions. It's pronounced with a V, even though it's spelled with a W. Wittig, who is a person. The Wittig reaction, we're not going to look at the mechanism for this reaction. It's pretty tricky. The Wittig reaction uses a ketone or an aldehyde with this particular reagent, which is called a Wittig reagent. Notice that it has a carbon-phosphorus double bond. Some books, some resources are going to write it as a carbon-phosphorus single bond with charges on the carbon and the phosphorus. I personally like to look at this form better. It makes it easier for me to predict the products of this reaction. So regardless of which method your book uses or whatever you're looking at, if you see that carbon, if you have a carbon-phosphorus single bond in your mind, imagine it as a carbon-phosphorus double bond. So like I said, I'm not going to go over the mechanism for this reaction because it's super complicated. We're just going to learn how to predict the products. In this reaction, the Wittig reagent, this guy right here, is going to be split at the carbon-phosphorus double bond. And half of this Wittig reagent is going to be put onto the carbonyl carbon. The double bond is still going to be there in the original molecule, but instead of this being a double bond to an oxygen atom, it's going to be a double bond to the non-phosphorus portion of the Wittig reagent. So this part that I have in the box. This is a carbon right here, which is double bonded now to this what used to be the carbonyl carbon, and that carbon has a hydrogen on it and also a methyl group. So what I've done is I've just taken this portion right here and I've essentially traded it for the oxygen on the carbonyl group. Now, you do have to, whenever you're making an alkene, you do always have to pay attention to the formation of cis and trans isomers. It is kind of weird when I'm like going back and forth between line notation and condensed notation. So I'm gonna squeeze the CH3 group in there just to make it not quite so weird. So this molecule has got two different products, a trans isomer and a cis isomer as well. And we can make predictions about major, minor. Just looking at the steric hindrance, we want our larger groups to be trans to each other. This guy right here would be major. Here's another one. Again, we can practice predicting the products here. We are going to keep the double bond, but instead of it being a double bond to an oxygen, it's going to be a double bond to the non-phosphorus half of the Wittig reagent. That's a carbon atom with two hydrogens on it. Right there. No cis-trans to worry about with this one. Sometimes you might see a Wittig reaction written like this one right here. This is kind of like a Wittig in disguise. We have our aldehyde, so I'm just going to begin by drawing that aldehyde. Remember, we're going to be replacing this oxygen with the non-phosphorus half of the Wittig reagent, but where is it? So these steps here are actually showing the formation of the Wittig reagent, and sometimes you'll have that written out instead of just them giving you the structure of the actual Wittig reagent. So the a Wittig reagent is formed between an alkyl halide and this PPH3. pH is our abbreviation for a benzene ring. And so what you just need to do is kind of envision what that Wittig reagent would look like. We would have our PPH3, and if we're looking up at this as sort of like our guide, that PPH3 has a double bond on it, and the double bond goes to the alkyl group. Boom, here it is right here. A carbon with a CH3, and you just have to be a little bit careful about like what's the correct number, what's the appropriate number of hydrogen atoms to have on this carbon. This carbon has 2 bonds to the phosphorus plus 1 bond to this CH3 group, so this carbon is just a CH. Lost one of its hydrogens in the process. So when we look at this guy right here, we want to imagine like what's going to be attached to this. It's going to be the non-phosphorus half of the Wittig reagent. That's a C HCH3, plus also don't forget the other isomer, CH3 on the left, hydrogen on the right. Is that the exact same? Look at that. That's the exact same thing as what we did up here. Not very, oh no, it's not exactly the same. It's almost exactly the same. Last thing that we're going to look at here are forming these particular alkenes using the Wittig reaction, so making a prediction about how you might do this. To do a retrosynthesis, what you're going to do is keep in mind that the Wittig reaction actually creates this carbon-carbon double bond, so that means that our original molecules are going to have the same number of carbon atoms, but the double bonds are going to be attached to something different. And this to me looks really kind of kooky, so I'm going to put these hydrogens in here and then put the hydrogens over here just so that I'm not confused about what's going on. So these are the two main components of this reaction. One of these components is an aldehyde or a ketone. The other component is the Wittig reagent. And much like a Grignard reaction, it doesn't matter which is which. We could just choose whichever one we wanted. So I'm going to make the one on the left my aldehyde. This is going to be an aldehyde right there. And then the one on the right is going to be my Wittig. So I'm going to initially fill that in with just a PPH3. Now this problem did specifically say to take it all the way back to an alkyl halide, which means we're trying to replicate this sort of a thing right here. So I want to show how this guy gets formed. This guy gets formed between PPH3 and butyl lithium, BULI, which is like the base that helps this reaction occur, and then some sort of alkyl halide coming from the carbon portion of the Wittig reagent. The alkyl halide needs to have just one carbon in it, and I can see that it's got two hydrogens in there, so I'm going to draw those two hydrogens in. It needs to have a halogen. I'll just make a bromine, and then we need to fill in as many other hydrogens as necessary to make sure that this carbon atom has enough bonds. CH3Br. We've got one last example of this. So here is the carbon-carbon double bond that is being formed in this reaction. I'm going to begin by splitting the molecule at the carbon-carbon double bond. So we've got one half right here, and then the other half right here. And one of these portions of the molecule is the aldehyde or ketone, and the other portion of the molecule is the Wittig. We can choose which is which. This time I'm going to mix it up. I'll go the other way. So I'll say this is going to be my ketone in this case. And the other reactant that I have over here, this will be my Wittig, PPH3. So now I need to show how this PPH3 gets formed. This is a reaction between PPH3, the base butyl lithium, and an alkyl halide that involves this many carbons. So let's see what that alkyl halide might be. We've got this carbon atom right here. That's this guy right here. It has one hydrogen on it already to begin with. It needs to have a halogen on it for this reaction. And then we've got to fill in one more hydrogen just so that that carbon is happy. Looks kind of funny to draw it like this, but this is the correct structure of the alkyl halide.